in a certain reaction. So if I give you a chemical reaction, there may be one reactant that limits the amount of product that can be formed. So in the example of the bikes we talked about, if you were given 2 wheels and 6 frames, the wheels are still going to limit the amount of bikes that can be formed. Okay, even though you have more than enough frames, if you only have 2 wheels, you can only make 1 bike. The reactant in short supply is called the limiting reactant. Okay, so think of limiting in that it limits the amount of product that can be formed. So let's look at a limiting reactant example, this time with a cheeseburger. Okay, so you always have to have some kind of equation. Okay, remember that your reactants are on the left side, your product is on the right. So when we talk about limiting reactants, we're trying to figure out which piece of the left side is going to limit the amount of product that's formed. So given this equation where it takes 1 bun, 1 meat patty, and 1 slice of cheese to make a cheeseburger, if I had 3 buns, so if I had 3 of this reactant, 2 burgers, and 4 slices of cheese, how many actual burgers could I make? Right? 2. Why? Okay, we only have 2 patties. So in this case, this reactant limits the total production of burgers. Okay, we would call this the limiting reactant because this reactant, this part going in, limits the total product. Okay, so you would have that, and then we would have some things left over that wouldn't get used. Let's look at another example, but this time we're going to use atoms. Okay, so here we have calcium atoms and sulfur atoms. It just so happens that they combine in a 1-to-1 ratio. Okay, I think we're pretty straightforward. 1 calcium will bond with 1 sulfur to form a molecule. So if we had this many atoms and we were to pair them up, we would find that we could make 7 total molecules, but there would be 3 extra of our sulfur. Okay, so in this case, because we run out of calcium first, it all gets used up in the reaction. Calcium would be the limiting reactant. The theoretical yield, or the amount of product that could be produced, would be 7 of them. And what is left over, we just call the excess. Okay, we don't need to focus on that term, but excess means extra, meaning that doesn't actually get used up in the reaction. Okay, so the 2 key words here are limiting reactant, and then we have to understand that theoretical yield in this case is going to be limited or determined by the limiting reactant. All right, so here's an example where it involves a limiting reactant. So first of all, how do you know when you have a regular problem versus a limiting reactant problem? Your regular stoic problems, where you start with one thing and go to one product, they will only have one given value. So if you only see one number in the problem, it's just like we've been doing. But in this case, we're given 2 known values. So it says, what is the theoretical yield? Okay, so again, we're going to find how much product is formed of ammonia gas, which happens to be this. Okay, we're going to try to find how much ammonia gas is formed in the reaction between 5 grams of nitrogen gas and 5 grams of hydrogen gas. So this time we're not told that we just have nitrogen and we have excess hydrogen. Okay, so what we need to do is we need to figure out how much product will be formed by this reactant. And then we're going to do the same thing over again, where we're going to figure out how much product is formed by this reactant. Then we're going to compare what we were able to produce and decide what the true theoretical yield is based on that. Okay, so identify a limiting reactant problem because it has 2 known values. As soon as you know you have two known values, you're going to have to do two stoichiometry problems. So yes, even more work for one problem. So let's start by balancing our chemical equation, because we still always have to do that. I'm going to need a 2 here and a 3 here to balance that. Okay, I'm going to switch to the next slide just because this is all at the top. Okay, the goal here is still to find the theoretical yield, the grams of product formed. So, two separate problems. First, we're going to ignore the hydrogen. We are going to go from here to here. We're not even going to pay attention to that. So in case you need a refresher, we start with the grams of our reactant. We turn those grams into moles. Bring grams down. We look that mass up on the periodic table, which is going to be 28.02, and that is always in 1 mole of that substance. Okay, our second step is always our mole to mole ratio. Okay, remember this unit determines what's on the bottom, and we turn it into moles of our product. The numbers that go here come from the coefficients in the problem. So in front of N2, there's no number written, so it's a 1. In front of NH3, it's a 2. And last but not least, we turn our moles of this substance now back into grams of that substance. Once again, using the periodic table, 14.01 plus 3 times 1.01 is 17.04. Okay, 2 sig figs. So this is going to produce 6.1 grams of NH3. Okay, so if we only had information about nitrogen, we would know that this is the theoretical yield of ammonia, which happens to be NH3. Okay, but we don't know which one of those two known values is going to produce more or less product. So now we're going to do a second problem within the same question. Green, sorry, so this time we're going to work with our other reactant and we're going to go to our product. Okay, so we're going to ignore that piece of information. It just so happens they were the same number, but that's not always the case. Okay, so now we're going to see how much actual product we could form from the hydrogen. Okay, so think of this as like the buns, and now we're calculating for our burgers. And if we had to, we would do a third one for the cheese, but we don't need to because there's only 2 reactants here. Grams of H2 comes down. We're going to turn it into moles of H2. Grams comes from the periodic table, always in 1 mole. Next comes your mole to mole ratio. You will always turn your reactant into a product. Okay, so you're always going to end up with whatever the product is. 3 moles of H2 to 2 moles of NH3. And now turn those moles of NH3 back into grams. Notice the last piece here is the same for both because we changed our reactant into the same moles. Okay, now we do the math on that one. And again, to 2 sig figs, we're going to get 28 grams of NH3. All right, so now you can only have one answer to this problem, but we did two calculations. The theoretical yield is the actual amount of product that would be able to be produced in this reaction. Which one of these is going to be the amount that I can truly form based on those products or reactors? So what? If I have 2 burgers and 3 buns, would I be able to form 3 cheeseburgers or only 2? 2. Okay, so here's what the issue is. This amount of product is going to form, but then we're going to run out of N2. So are we ever going to get to 28? No, we don't have enough. What'd you say? You can make it bigger. Good, but in this case, we can't. Okay, so you will never get to the higher amount. Okay, so theoretically, from that, you could get to this. But because we're going to run out of this reactant first, it is always the lower amount of product formed that is your theoretical yield. Okay, so theoretical yield in a limiting reactant problem is always the lowest or smallest amount of product, smallest product formed. Okay, so you still go through the math, you still do 2 separate calculations as if you had 2 different problems, and then you pick your smaller number. Along with limiting reactant problems, not only do they usually ask you what the theoretical yield is, this would be your answer, but they will usually ask you what was the limiting reactant. So when they ask you that question, you have to remember what your reactants are. Here was one of your reactants. Here was your other reactant. Which one of those 2 produced the least amount of product? Which one limited the amount of product that could be formed? Ethan? N2. Okay, so if you were asked what the limiting reactant would be, it is N2. Okay, a reactant is a thing. So you are listing the reactant in the problem that created the least amount of product. A theoretical yield is a number. So you're going to say how much of your product was produced. So the math is not different here. You just have to do it twice. Then you have to choose the correct product and list the limiting reactant. Question. Everyone know where we are? Top of the very last page. Top of the very last page. Okay, so what will usually happen is you'll be given a regular stoichiometry problem, either a limiting reactant or a regular. Okay, in this case, it is a limiting reactant problem. How do I know this is a limiting reactant problem? Okay. Because there's 2 numbers in the problem, 2 knowns or 2 givens. Okay, so that means it says 0.31 grams of hydrogen gas reacts with 1.2 grams of oxygen gas. What is the theoretical yield of water in grams? Okay, so we want to find water, but again, since we have 2 knowns, we have to do 2 separate stoich problems and figure out which one's the true theoretical yield. Okay, then we're going to go on and introduce something called percent yield. So here's your second example of a limiting reactant problem. Okay, so we're going to start with this information and we're going to go here. So 0.31 grams of H2, 2.02 grams of H2 and 1 mole of H2, 2 moles of H2 to 2 moles of water, 1 mole of water has a mass of 18.02 grams. Okay, I'll calculate that one in a minute, but now we're going to do the other one from here to here. So 1.2 grams of O2. That's 32 grams of O2 in 1 mole of O2. 1 mole of O2 to 2 moles of water. And in 1 mole of water, there are 18.02 grams. Okay. And some of you calculate this bottom one while I do the top one, and then I'll ask for your number to save a little bit of time. Okay, so 2 sig figs up top here. This is going to be 2.8 grams of water formed. Did anyone get the bottom one? Go ahead, Red. What is it? 1.3. Do you agree with that? Oh. Oh, we are on the very last page at the top. Okay, so 1.3 grams of H2O. All right, so we did both the problems. The question is, what is the theoretical yield in water in grams? So we can't just leave it like this. We have to choose an answer, which is the correct theoretical yield. 1.3, we picked the smallest one. Okay, so this is my theoretical yield. What is the limiting reactant in this case? O2. Yep. Okay, so the limiting reactant is the reactant that creates the least amount of product. So I'll just put LR for limiting reactant. And now is the problem before. I apologize for being out of order here. Okay, so you're going to go to the side called percent yield. Percent yield is just a percentage. Okay, so we're going to take some partial value divided by some whole value. What are those values? In percent yield, yield means how much is formed. We want to figure out how close an experimental amount or an actual amount formed in a lab is to the theoretical amount, which is what you calculate. Okay, so compare an experimental or actual amount to a theoretical amount. Percent yield is just your actual yield or actual amount of product formed divided by the true amount that should be able to form theoretically based on your calculation times 100. Yeah. Exactly. Okay, so theoretical yield is what you calculate. So whatever you calculate using your STOIC will always go on the bottom. The top number has to be given to you. Okay, so for example, here's just those terms that I already put for you in your packet. Actual yield is the amount formed during an experiment. Theoretical is what's predicted in your STOIC calculation. Okay, so there's 2 ways you might see this. Number 1, this is the easy way. A problem will literally give you your experimental yield and your theoretical yield. So it says if a student actually produces only 10 grams of product in the lab, when the theoretical yield was calculated as 11.25 grams, what is the student's percent yield? Okay, so we know that percent yield is equal to actual over theoretical. So in this case, it said you could actually produce 10 grams in lab, but the theoretical yield was calculated to be 11.25. So we take the actual divided by the theoretical times 100. And again, we always do that times 100 to turn it into a percent. Otherwise, it is just a decimal. And 4 sig figs would give us 88.89%. Okay, so that's pretty high yield. It means in the lab, I was able to form pretty close to what I should have been able to form. The way you will usually see this, however, is you will be given the full stoichiometry problem, like I had already done with you. Okay, so this is what we already did. And then there will be a second part as a follow-up. Okay, so that was just the work. Okay, so now here's the second question based on the work that we did. So now you're back over on the last page. I apologize. Okay, so now below the work for example 2, it says, if we do an experiment in lab and only produce 1.28 grams of water in the reaction, what is the percent yield? Okay, so we formed water. Boom, here was our work. We determined the theoretical yield. Boom, right here. Yes. Oh, probably because I went to a different number of things. No, 1.38 is the, oh, thank you. 1.38. Couldn't figure out where you were. Okay, so we were able to produce 1.38 grams of water. So that is our actual yield because we did an experiment in the lab, 1.38. Theoretically, we should have only been able to produce 1.3 times 100. It is possible to get more than 100% yield, okay? Because again, contamination or things could happen. 1.38 divided by 1.3 times 100. Okay, so I'm not going to worry about sig figs here just because I don't want to confuse everyone. But this shows us that in lab we were able to produce 106%. Okay, again, lab error can cause all kinds of things to happen. So you may have less than 100%, you may have greater than 100%. It can go either way, but you put your actual divided by your theoretical. The one from the calculation always goes on the bottom. Okay, I know that was a lot real fast, but again, it was not much new stuff. Primarily, we still just did stoich. We know now that the theoretical yield in a limiting reactant problem is the lower amount. The limiting reactant is the reactant that produced the theoretical yield, okay, because it limited the product. And percent yield is just the lab amount divided by the calculated amount times 100. Okay, so here's